the previous lecture we elaborated on how to use various types of elements and the families of shape functions defined over these elements in a two-dimensional finite element computation. So we had talked about a domain as a sample example, which is rectangular, where we had chosen either to make a mesh of triangles or a mesh of quadrilaterals, which in this case would be rectangles. And the convention we had followed, this is my edge 1, boundary edge 1, boundary edge 2, boundary edge 3, boundary edge 4, same thing. Okay, let's say that I would like to do a quadratic approximation in either of the cases. So here I will use quadratic triangles, and here I will use quadratic serendipity. Okay. So if I do quadratic triangles, so I will do the numbering in my particular way: 1, 2, 3, 4, 5, 6, 7, 8, 9, and the mid side ones I'll call this 10, 11, 12, 13, 14, 15, 19, 20, 22, 23, 24 and 25. So as I had discussed last time, that the corner nodes of the elements of the domain, the vertex nodes, will be given the degrees of freedom first. That's my convention. It has its advantages. Then we'll name, after that we'll name the side degrees of freedom element by element. So first I go to the first element, number the degrees of freedom corresponding to that element, then the second one, and so on. So here I have 25 degrees of freedom. If I use the serendipity, here again I will have these 9 corner ones, and then we will start numbering the edge ones. So edge in this element I will have, this is 10, 11, 12, 13, 16, 17, 18, 19, 21. So in this case, in the case of serendipity, I have a total of 21 unknowns, and in the case of the triangles we have 25. Now let's talk about the boundary conditions. So I could have edge 4 has u specified, and maybe this edge 2 will have some variation of g, which is the flux. Okay. So these are the boundary conditions that I may have for the problem. Now given these boundary conditions, given the domain data, do I know what is the smoothness of the solution. So solution to the problem, exact solution, is U. The question is, how smooth is it? By how smooth we mean that how many derivatives of this function U, x and y derivatives, are going to be bounded. That is, they will have finite values. Okay. It turns out that the smoothness of the solution not only depends on the body source term R and the boundary flux term G, or the boundary displacement which is here U bar, but it also depends on the domain and the way the boundary conditions switch. Okay. So if now the solution is smooth, let's say in this case the solution is smooth, U is smooth, then we will be interested in knowing how well is my finite element solution performing, okay, as compared to the exact solution. So we will be talking about U minus U finite element, which we are going to call as again our error. This is error in the current finite element solution. Okay. So I have put one mesh, I have taken one approximation, solved for the finite element solution, and now I say, okay, what is the error? This error is represented as E. So now we had said, how are we going to measure the size of the error? We said the size of the error will be measured in terms of square root of some factor into the strain energy of the system. Okay, we are more familiar with strain energy kind of terms. So here what we are going to define, as we had done earlier, BUV from our variational formulation of the weak form is the integral over the domain omega of, as we had put, K11 del U del x plus K12 del U del y into del V del x plus K12 del U del x plus K22 del U del y del V del y di. Okay. So we are defining this bilinear form, if you remember what we had done earlier, in terms of this quantity, which is nothing but the right hand side of our weak formulation. So then I can define what is BUU. Okay. Similarly, I can define what is BUFE comma UFE. Okay. Now UFE will have you see that here the integral over the omega will be understood in terms of sums of integrals over each of the elements. So similarly, by as we have done here, now by doing this element by element sum, I can define B E comma E. Okay, and we had said that we will define the size of the error in terms of what we call as the energy norm of the error. Let's give it by 2 lines, defined over the whole domain, which is our domain is this one. This is my domain omega. Okay. So it is defined over the whole domain. This thing is equal to nothing but square root of B E comma E. Okay. So we are going to define this quantity, which is energy norm of the error. Why are we calling it energy norm? Because it is in some way related to what we know as the strain energy. Though this is not a problem of mechanics, but we define it like this. Okay. So once we have this energy norm defined, then the question is that, okay, with respect to this quantity, what do I expect? If my UFE tends to, when u finite element tends to u implies the error tends to 0 implies the energy norm of the error should tend to 0. This is what we mean by convergence, that okay, I refine my approximation in some way, and when I refine my approximation, the error should go down to 0. Now we measure it with respect to the energy norm. Okay. So now the question is, how do you refine the approximation? So in refining the approximation, we could do two things. We could either decide to refine the mesh, that is, break the existing elements into smaller pieces, uniform smaller pieces. Okay. So this will be my new mesh, which will have 1, 2, 3, 4 into 4, 16 elements. So out of a mesh of 4 elements here, I have 16 elements. If I have to do it for the triangles, I will break the existing triangle into 4 equal triangles. Okay. I can keep on doing it. Then the mesh is getting refined. And here again, like in the 1D case, we will have to define a mesh size. So mesh size is nothing but, we will say that we will take this horizontal length h. Okay. So for the smaller mesh, the mesh size is less than the bigger mesh. In fact, it is half of that of the bigger mesh. So h new is equal to half of h old. Okay. So this is what we mean by enhancing our approximation using mesh refinement. So this is called, as we had discussed in the 1D case, we are going to be specifically talking about the h version of the finite element method, where improvement in the solution is achieved by keeping my p fixed, that is the order of approximation fixed, and only refining the mesh. Okay. So let us see now, we would like to have, obviously if the mesh is getting refined, we will like to have a measure of this energy norm of the error in terms of, as a function of the h, the mesh size, and we expect that as the size h goes to 0, this should also go to 0, and at what rate? In the 1D case, we had some rate. Let us see what we have here. So when the u is smooth, it turns out that this quantity goes as some constant into h to the power of p, where p is the order of approximation that we have and h is the mesh size. You see that this is exactly like what we obtained in the 1D case. Now, when the solution is unsmooth, so let us see what kind of unsmoothness are we talking about. In that case, let us remember that throughout we have been only talking about polygonal domains. So let us take one polygonal domain, which is like this. Okay. Let us say that what I am doing is I am fixing it here and here. Here I am giving a flux condition, okay, some flux condition, and here I am also giving a flux condition. Okay. Let's say I may also have a flux condition here in this part, while here I am fixing the solution. Okay. So whenever I am drawing this, this is, I will say u bar is equal to 0, here also u bar is equal to 0, and here let us say g is specified, here also g is specified. Okay. Now how do I solve the problem over this domain? Well, I could make a mesh of triangles or quadrilaterals as I wish. Okay. So I make some kind of a mesh here. I'll first make something, then we'll talk. Okay, so let me make a mesh of triangles. It doesn't matter whether you have a mesh of triangles or square or quadrilaterals. It will always, whatever we are discussing is going to be the same, applicable to both cases. Now, if I solved with this given mesh, so we will say the mesh size is essentially the maximum of the, let's say, the length of the edge of an inch square of one of the triangles, because here you see the sizes of each of the triangles may be different because I have an irregular domain. What happens then, you will see that in this case I have these points which are interesting points. What happens if I look at it, imagine as a problem of elasticity, and I fix the displacements here and I have this kind of a corner, I expect stress concentrations to happen. Similarly, at these points A, B, C, C also, because here the boundary condition is changing, suddenly switching. So I have one flux condition and suddenly I am fixing the displacement. So at these points I would expect stress concentration to happen. Similarly, for this the single variable problem also I would expect the flux or the derivatives to become high in the vicinity of these points. In fact, they are not only going to become high, but they are going to become infinite. That is, we are going to have singularities in the derivatives. Okay, that is, here in the vicinity of these corners I am going to have a singular behavior of the solution, and then the singular behavior will very quickly die away. That is, it is localized in some vicinity of these corners. Okay. Because of this, the question is that can we characterize the singularity? It turns out that yes, in the vicinity of these corners I can characterize the singularity. How? By, let's say, I take a generic corner. Okay, this is my generic corner O. Let's say now I fix an axis. Okay, with respect to this I measure for a given point P in the vicinity of this, I will measure this angle theta and the length r. That is, I am using a local polar coordinate system in 2D. Then the solution in the vicinity of the point O will be essentially u is a function of r and theta in the vicinity of point O, okay, is essentially some constant into r to the power of alpha into some function of theta. Okay, it turns out that so this is how the solution in the vicinity of this corner is going to look like. This is obtained from an asymptotic expansion. Okay, in fact this expansion is not only one term, there is an infinite series in terms of many of these alpha i's, but this is such, we are taking the first term which corresponds to the smallest alpha. Okay, because that is the one which dominates the whole behavior. Now it turns out that when this angle omega is greater than equal to 180 degrees, okay, then alpha is less than 1. So if alpha is less than 1, what happens to del u r? Del u del r? Del u del r will be a1 alpha r to the power of alpha minus 1. So now you see into f of theta. what has happened, this del u del r is now r to the power of alpha minus 1, where alpha minus 1 will now be less than 0. So as my r comes down to 0, this quantity shoots up, that is, this becomes singular at r equal to 0. So this is the nature of the solution in the vicinity of these corners for which angle is greater than 180 degrees. These corners are called re-entrant corners. Okay, so this kind of a corner is called a re-entrant corner. Okay, so let me go back to our figure. So corresponding to each of these corners, I will have, by doing a local polar coordinate, putting a local polar coordinate in the vicinity of the corner and doing an expansion of the solution in the vicinity of the corner, I will have for each of the corners a corresponding exponent of that r to the power of alpha term here. Also you will have r to the power of alpha c. Okay, so I'll have all these exponents. Okay, now if I go and take the minimum, I'll say alpha is equal to the minimum of all these alpha a, alpha b up to alpha, I may have alpha e. Okay, then in terms of this alpha, if I go and do a mesh refinement for the given domain, okay, it will turn out that the error is essentially of the type c h to the power of mu, where mu is equal to minimum of p and alpha. So what has happened here? The convergence, the rate of convergence is now driven by the smoothness of the solution, that is, by the exponent of this r to the power of alpha term in the vicinity of the corner, of the re-entrant corners. Okay, and my domain may have multiple re-entrant corners because we face this kind of domains all the time. Okay, these are quite common in engineering practice to have this kind of domains. Okay, so we are going to have this, and then it doesn't matter what p you use. Okay, the rate of convergence is always going to be minimum of p and alpha. So if I use a higher alpha p, still I'll get the rate of convergence is alpha if alpha is less than p. Okay, which is now a so-called suboptimal rate because raising the p has not helped us. Okay, so then the question is, how do I do a better job? Okay, to do a better job, let's go back to our problem. It's quite obvious that here we are not able to capture the singular behavior because of these large element sizes. Okay, so what we should do is we should do a proper refinement of the mesh in the vicinity of this corner. Okay, which so that I can capture the singular behavior of the solution. It will not be captured by just raising the p, but you have to do a refinement of the mesh. And what we are going to do is we are going to do a so-called geometric refinement of mesh in vicinity of corners. Okay, so how do we do it? So let's go back to our domain that we have made. I will make this domain again. Okay, so what we'll do is we had a problem areas were these points. Okay, So what we are going to do, in the vicinity of these points we are going to take these rings. They need not be rings, they could be approximated by polygons. Now of some size, let us say this is of size some h, some initial h. Inside this ring, so let us say this is of size h initial. Inside this ring, so I am going to now make smaller rings. Okay, that is, I am going to make a smaller ring such that if this is a distance h from the point of interest, the singular point, then this is at a distance hq and this is at a distance hq squared, and so on. I can have n rings where the nth ring will be at a distance hq to the power of n, where q is essentially taken to be generally 0.17 or 0.15. Okay. If I do this, then I can make these rings in the vicinity of these corner points. Then in these rings I can now make the elements. Okay. So I can make my elements in the rings, and as I said, the rings need not be circles, they could be approximated by polygons. Okay. So I make these triangular elements here, somehow finish them off, okay, and then extend the mesh outside. Okay, so on. So I will be getting my mesh like this. So in the vicinity of the corners I make these geometrically refined meshes. Okay. Now once I do that, elsewhere outside these corners I can put large elements, nobody stops me from there. So I am making a non-uniform mesh, non-uniform mesh. Then we can show that in this case, if I take sufficient number of rings, then the energy now of the error will now go as C n to the power of minus p by 2, where n is the number of degrees of freedom. Okay. This is now optimal for the H version of the finite element method. Now I can use a combination of H and P. Okay, that is, I start raising the P. So here if you see this, in the vicinity of the corner the solution is singular. Okay, so here if I take these refined meshes and a low P and I keep on raising the P such that far away the solution, away from the corner the solution is smooth. Okay, solution is only unsmooth in the vicinity of the corner, then in that region using large elements with high P will give very good accuracy. Okay, and that is exactly what we should do, use large elements here with high P, small elements with low P, then in that case we can get essentially exponential accuracy. So when we do HP version of the finite element solution, okay, then I can get exponential accuracy. Okay, let us go back and discuss yet again that okay, in real life structures or components that we have, we will never have these corners. We will have in fact a fillet here, that these corners will be rounded off. Okay. But when we are making a mesh to represent this domain, see finally the domain is discretized. It is represented in terms of a mesh that we put and the approximation which goes with the mapping that we use. So when we put the mesh and when we use the mapping, that is if we use this linear mapping, then this fillet will be represented by these corners. So even though my actual problem does not have a singularity per se, though it has a stress concentration, the problem that my finite element formulation sees is a problem with a singularity, and that's what it tries to solve. Okay, and for that we are still going to get the same problem as we have outlined. Okay, so now so this was about various ways of doing basically controlling the accuracy of my approximation. Another issue that can crop up is, one may say that, okay, I am really not interested in what is happening here, I am interested in what is happening here. I am interested in a region which is far away from the boundary, from any of these singular corners, because that's what may be my region of interest. For example, I may have a cutout here, I may be only interested in the vicinity of the cutout. Okay. The question is, then do I have to do all this business of refinement and all those things to get accurate solution here? Okay. In principle, from the physics, it looks like no, that really the effect of the singularities is local, and this effect dies off very fast. Okay. So away from the singularity, the solution is smooth, everything should be fine. But unfortunately, in the finite element solution that we get, okay, so I will draw now a domain with one re-entrant corner. I am interested in this region. If I look at how do I measure the accuracy of the solution here, if I am interested here, so I will talk of again the same thing, energy norm of the error now in this subdomain or the region of interest omega naught. Okay, you will see that this error goes as Ch to the power of mu 1, sorry, mu 2, because I have already used mu 1, so let us talk of mu 2, where mu 2 is equal to minimum of p and 2 alpha. Okay. So if my p is less than 2 alpha, I am fine as far as the accuracy here is concerned. It goes at what I got for the global optimal rate. But if my 2 alpha is less than p, that is, I have used high enough p, and in most of the engineering problems this is always true, even for p equal to 1, because generally for the domains I have shown, alpha could be 2/3, 1/3, and so on. Okay, so for the 1/3, 2 alpha is always less than 1. So in that case, the effect of the singularity here dominates the accuracy of the solution here. Okay, this is called so-called pollution effect. That is, numerically, whatever was the mistake, the penalty that I paid in representing the solution at in these unsmooth regions, that penalty I have to pay everywhere. Okay, that's why this 2 alpha comes into play. Okay, so even if I am interested in this region, I will have to do the mesh design in such a way, near the corners, in such a way that this influence of the singular term becomes small here. Okay, so the refinements have to be done there, and this is one of the drawbacks of what is known traditionally as a global local methods, where this was traditionally ignored, that you didn't care about refining the mesh at singular points which are far away from the region of interest, but you have to do it because it directly affects my solution, the numerical solution. Okay, so this is about mesh refinement that we can use in order to get better approximation, okay, or better quality solutions. Now what happens with the p version of the finite element solution? In the p version, when the solution is smooth, that is, I don't have these singular points, etc., then I get exponential rate. of convergence. When it is singular, what do we mean by the p version is that I fix the mesh and I raise the order of approximation. Then you will see that the error n to the power of minus p essentially. That is, it goes it goes as n to the power of not minus p, it is minus alpha by 2. Okay, so error again goes essentially, if I have the equivalence with the h version, as h to the power of alpha. Okay, so here also in the p version, the error, it does not do better than what you have for the h version. Okay, only thing is that the constant may be small, constant in front. Okay, now let's talk of a different thing. So this is essentially how we should do the mesh design, etc., and with that we can control the accuracy of the solution. Now I have solved the problem. I would like to now obtain the flux information or the derivative information out of the solution of the finite element problem. How do I obtain that? So in that case, we will have to talk about post processing of the solution. Okay, so given the mesh, given the domain, let's say I am interested in the values of del u del x, del u del y here in this element. How do I use my finite element data to get a better value of these things, that is better with respect to the exact solution? Okay, because the finite element solution as such, if you see, it will have jumps in these quantities at the interface boundaries. Okay, so while the exact one is nice and smooth. Okay, so what we would like to do is obtain a better information about this data at this point. So one thing is directly use data from Gauss points, which is especially true for the quadrilaterals. Okay, while for the triangles, if I have the region in the vicinity of the centroid could be used, the centroid or the region in the vicinity of centroid can be used to obtain the better values of this derivative information, which is not always true, but in many cases this is quite good. So this is just the use of the direct points from the mesh that we have or from the element in order to extract data at these so-called good points. Okay. For the elasticity problem, this is not going to be true, as we will see later on, but for this problem these points are good enough. Okay. If I want to recover good values for the whole element, okay, then in that case, if you remember in the one-dimensional case, we had talked about this super convergent recovery techniques, that is by fitting the finite element data over a neighborhood of the element of interest, we can extract seemingly better representation of the derivatives. Okay. So what we can do here is, so we will take this neighborhood. If I am interested in this element, we will take a neighborhood of this element, a one element neighborhood, okay, which incidentally in this case turns out to be the whole domain, whole mesh. Okay, but depending on the element, so we take all the elements that are connected to this element, that is they share either a vertex or an edge with this element. Okay. Now over these elements I can have a very simple fitting that we talk of del u star del x with respect to the element of interest tau is equal to sum of aij x to the power of I y to the power of j, such that I plus j is equal to 0, 1, 2 up to p. Okay. So this represents essentially the polynomial of pth order. Okay. A general polynomial, sorry, we will have p plus 1 where p is the order of approximation. P plus 1 or p will do fine because the finite element solution del u fe del x will essentially be a polynomial of order in the element of order p minus 1. So for this we take one order higher, we could take two order higher also, and we will take it as a polynomial of order p. This is my what I would like to obtain out of my finite element data. Okay. Then over this patch of elements, so we will call that patch in the previous figure as this patch of elements will be called p tau. This is my element tau. So this all these elements including the element tau is called the patch p tau. Then over this patch I will define J1 is equal to integral over the patch of del u star del x minus del u fe del x whole squared dA. Okay. This is what I am going to do, and I will find the coefficients aij such that del j1 del aij is equal to 0. That is, I find a minimizer of this functional that I have defined over the patch, and these, remember, are the aij's corresponding to the element tau. Okay. Similarly, I am going to define another functional J2 is equal to integral over the patch p tau of del u star del y, okay, minus del u fe del y whole square dA. Okay, and find the aij's in this case where, well, I will say del u star del y over the element tau is equal to sigma, again I plus j is equal to 0, 1 up to p of bij x to the power of I y to the power of j. Okay. So over all these monomials, so if just to avoid confusion, it will be b0 plus b 10 x plus b 20 x squared plus so on plus b11 xy plus b01y plus so on. This kind of a expression it will have. Okay, so it's in terms of all the monomials of order up to p. Then we want the bij's to be such that del j2 del bij for the element tau is equal to 0. So this will give me the equations in terms of these coefficients bij. Similarly, the previous one will give me the equations in terms of the coefficients aij. Solve these two at the element level, and this is going to be a very small problem. The size of it is going to be simply p plus 1 into p plus 2 by 2 for each element. Okay. So these small problems can be easily solved, and I will obtain the set of coefficients aij for the element tau, bij for the element tau. Using this set of coefficients, now I'll go back and construct my del u star del x in the element. So I'm doing this projection over the whole patch, but I use the data only in this element. So now if I have to go and do it for the next element, let's say I'm interested in this element, okay, then the patch for this element will contain all these elements. Okay, I'll do the same job for the next element by taking this patch and constructing these coefficients aij, bij, and out of that I get del u star del y and del u star del x for that element. Okay, so once I have this information, then I can use this information del u star del x in the element tau and del u star del y in the element tau as recovered derivatives. Okay, and in terms of these derivatives, I can define the flux quantities q1 as k11 del u star del x plus k12 del y over tau. So this is a simple recovery procedure with which we expect to get better flux quantities. And in general, for meshes which are not too distorted, elements which don't have very small or very large angles, okay, in that case this does a pretty decent job of giving us a recovered stress field. Okay, this we can talk of as one of many methods which are now available to do this kind of a post processing. It is a patch recovery approach. We can define various other definitions of this J1, J2. We can do recovery of directly the flux terms, that is Q1 star, Q2 star. We can write those in terms of polynomials. We can do so many things and get the recovered quantity of interest. Okay. So with this, we are now pretty much in a position to solve a finite element problem for this model problem that we have taken, which is essentially the generalized Poisson equation, which is applicable to the heat conduction problem, steady state heat conduction. Okay, it is also applicable to the torsion problem, where we are talking of the Prandtl stress function, which also could be written in terms of a Poisson or a Laplace equation. Okay, Poisson or Laplace depending on the boundary conditions we use. Okay, so all those problems can now be solved using what we have discussed. And remember that, for example, if we are talking of the torsion problem, then we may be interested in this kind of a section, cross section. Okay, and what do we do for such cases? We are talking, when we are talking of the shear flow and so on, that in these sections we know that there is going to be a stress concentration here. Okay, so how do we compute the so-called stress function zeta and the J, which goes into the modulus of the torsional rigidity Gj. Okay, so how do we compute these things? Now we can use our finite element method, solve this problem, which is a Poisson problem, that minus is equal to 2 with zeta equal to 0 on the boundary on gamma. Okay, solve this problem and we are done. Okay, from where we can get the J. You see here again there is a singularity in the vicinity of these corners for one of the very popular domains that we have, and this can be handled by doing mesh refinement in the vicinity of this. Okay, another section we are interested in is the I section. Again same problem. Here again we will have these corners and so on. Okay, so now we have a tool with which we can solve all these problems for polygonal domains. Next, what we are going to talk about is the case when the domain is not polygonal. Okay, So for example, I may have a domain which has a cutout, let's say circular or an elliptic cutout, or I can have a domain which has a curved profile. Okay. In this case, what we have to do as far as mapping the geometry is concerned, if we do what we had been doing till now, that is the linear map, then if I make a mesh, I will be only approximating these curves by straight lines. Okay. Let's say I make a mesh of triangles. So I will be only approximating these curves by straight lines. This is a bad idea, because depending on how coarse or how good is the mesh, okay, if the mesh is coarse, I will be making a lot of error in representing the geometry of the domain. Okay. So we would like to have a better representation of the geometry of the domain. So in that case, the linear mapping will not do, we will have to use a higher order mapping, that is mapping in terms of higher order polynomials. So we will be talking of so called subparametric isoparametric and superparametric maps. I will also indicate some special methods with which you can have exact representation of the contour of the domain if I know the representation, the parametric representation of the contour of the domain. Okay. So this is what we are going to discuss in the next class, and from there we are going to proceed to some other special problems like the elasticity problem, which is what is of great interest to many of us. Okay. Which now for the elasticity problem we will be talking of two variables, u and v, the two planar displacements, because we are talking of planar elasticity, u and v. So how do we go about and pose